Welcome to Labrats. Here at Labrats, we like to teach science or STEM here at our STEM Discovery Center. Science is this study of everything. Everything that we know about our physical universe. We use this process of science to study it. Today, we're going to focus on studying one of the most important aspects of life on Earth, the sun, and all that it has to offer us. Specifically, we're going to look at this light. Now, all this light gives us, whether it's food for all the plants, it allows us to see all the beautiful colors out here, or it gives us this heat and energy that we need to survive. Now, when we focus on the sun, the first question I always like to ask everybody is, what's the color of the sun? Because most people think it's yellow or orange, but actually it's white. It's pure white. What does that mean? White is actually every single color of the rainbow. Red, orange, yellow, green, blue, indigo, and violet, all shoved together. When they layer over top of each other, we see white. Now, I know you're thinking, it doesn't look white. Well, don't go look at it. It'll hurt your eyes. But we can't draw white on paper. So when we want to draw the sun, we're always going to go reach for that yellow because it stands out from the paper. Light is one of the most important things that we utilize here. Now, the reason science is so important is the study of science. As you start learning how this world works around you, it gives you the power to change the world. Thomas Edison changed the world by inventing the more modern light bulb. Now, we don't use those today. Those are really, really old. But we have been inventing new and better light bulbs ever since he first invented them, with a lot of other scientists' help. Today, let's use this scientific process to look at light a little deeper. Now, we know that sun is made up of all the colors of the rainbow. But what are these colors? Well, light is actually a wave. And what does that mean? Well, as light travels through the universe, it is traveling on a wave, having a wavelength and a frequency. It still moves at the speed of light. Each color that you can think of is actually its own wave. Every single color from red has the longest wavelength to blue, purple, and indigo violet has the shortest wavelengths. Without the sun, we couldn't even see these colors. When it's nighttime and we don't have any lights on, all we can see is black. We can't see any different colors. The sunlight and all the light waves that it gives us changes these colors that we see. This is the first experiment that we're going to look at, how this light travels from far off in space. I want to remember exactly how far the sun is. Well, I was going to say 8 light seconds from Earth, but this light originated from the sun. That is over 90 million miles away from us, or about 8 light seconds. As it travels here, it'll bounce off of our atmosphere, it'll scatter off of every single surface, and then eventually reaches back at our eyes, and this is what we see. The green plants, the yellow and purple flowers, all the colors that we see come from this light from the sun, or all the artificial light in these light bulbs of the classrooms. As this light is taking its pathway of 8 light seconds, hitting our atmosphere, it scatters across. Just like light through a prism or through the raindrops in the atmosphere to give us our rainbows, light will actually scatter as it travels through everything. Whether it travels through a window, a cup, a glass surface, anything. Let's examine how light gets affected when it has to travel through stuff. For this first experiment, we're going to take a simple cup of water and an index card and something to draw a simple arrow. Before you fill the glass, you can look at the arrow through the glass and see how the plastic can affect the look of this. It'll look a bit fuzzy, but it won't change the direction. As we filter in with water, now the light is going to go through air, plastic, water, plastic, and air. The light will now bend to the point where it completely switches direction. Our light gets manipulated as it passes through different objects. We call that manipulation an index of refraction. Now, we exist on Earth. We do not exist in the vacuum of space where light has nothing to go through. In Earth, we are covered in air. And in this air, there's actually a lot of dust. As this light travels over 90 million miles through space, through nothing, it eventually hits our atmosphere. Now, the reason our sky is blue is because our atmosphere is not only filled with air, but it's filled with dust, little rock particles, little dust particles everywhere. And as it hits these rocks, it scatters blue light, filling up our sky with the color blue. And this is actually what gives our ocean the color of blue. Now, it's pretty clear that if you pour a cup of water, water is not blue. So no, our atmosphere is not blue because of the ocean. Actually, the ocean is blue because of our atmosphere. This next test, we're going to see how light gets affected as it goes through different colors. Because every color of light is its own wave. When you see something that looks red, that's not because it absorbs red. Actually, it's because it reflects red. So all the other colors are being absorbed by this dye, and all that's left over from our white light is the color red. This is why we see red. All the colors come in, get absorbed, only red makes it back out. So as we start looking at other colors through these simple filters, you're going to see a surprising change. Some colors will absorb the wavelengths of light differently than others. So as we look through red, all of a sudden, almost all the oranges and yellows are invisible, and the blues and greens become black. For this next lab, give students more index cards and more colors. Tell them to draw whatever pretty picture they want, from a rainbow to a nice beach scene. This lab is all about filtering light through color. We can use physical filters, like this red light filter, or we can use water filters. We created these by just squeezing out Crayola markers in water. Or you can just use food coloring and our clear cup that we used earlier. A little bit of red, and all of a sudden you have a filter. Now, these labs are all about filtering through light. So what does it look like as we filter this light through our red lenses? Let's look at colors through filters. Let's try this red camera filter. See how all the colors change. Do they look the same? Does it all look red? Do some disappear or look black? What happened to the individual colors that you see? This is why we do not have red sunglasses. It would make driving almost impossible. We want to choose the color of our sunglasses to make sure that it doesn't change the way we see our world. It wouldn't help if we can't see the red of a stop sign. So that's why we choose specific colors like blues and browns and yellows for our sunglasses. This same idea of filtering and scattering of light gives us our beautiful sunsets. As the sun is up tall on the horizon, it scatters on the dust, creating blue. But as it goes far towards the horizon, it all of a sudden has to go through 10 times the amount of atmosphere. And as you're looking closer to it, all that blue light is scattering away. And what's left is all the reds, oranges, and pinks of a beautiful sunset. Everything around us is just an experiment of light. This is a fun filter cube called a CMYK cube. This has faces of cyan, yellow, and magenta that you can mix and match these three primary colors in a printer to generate any single color in the world. Now we can rotate this around to see all sorts of different cool colors. These are fun filters to see how we can use science to manipulate light. Now, in your home, you might have light bulbs that look different colors. Maybe one looks more blue, maybe one looks more white, maybe one looks more orange or yellow. Every single one of our lights, as we change the output of our lights, as we change how we make our light bulbs, it actually changes the colors that we see, spawning the internet craze of, was it blue or black or white and gold? This is why when you go to a department store and you buy and love this color of a shirt, when you take it home, you don't like it anymore, because we have different light bulbs than what you're gonna see out and about. This is why clothes can look different. Everything can look different depending on the source of light that we're using. How do we know what our source of light is? Well, only the sun is actually hot enough to give us the complete rainbow of all the colors of white light: red, orange, yellow, green, blue, indigo, and violet. It's over 10,000 degrees, giving us the complete visible spectrum. All of our light bulbs are actually just a small fraction of that light. Some are going to be more complete than others. Some, like LEDs, might only have 3 or 4 colors in them that look white. How do we know this? Well, we can make something called a spectroscope. You can buy one, or you can make one with simple everyday items. For our next lab, we're going to show you how to make a simple spectroscope at home, so you can actually see the components of color, the wavelengths of every single light bulb in your house. We use this same technology to look far deep in space at other stars, and we can tell exactly what creates that star, what elements are inside of that furnace that are thousands or millions of light years away. For this last experiment, we want to look at the components, the individual wavelengths that light bulbs and the sun can create. We use what's called a spectroscope. Now, this is one that you can buy for pretty cheap, but we can even make one that works just as well with simple materials. All you're going to need is a red cup, scissors, CD, cardstock. Business cards work great. This is an old flyer. To prep for this lab, to make this easier, first help your kids make a small hole through the top of the red cup, and we need just a piece of the CD. Now, you might notice the white coat is gone. Let me show you how to prep that. All we're going to do is take a CD and a pair of scissors and carefully cut a piece off of our CD. Once you grab a small piece like this, you're just going to use a little bit of tape, simple duct tape, and you'll peel it right off. Or knock everything down like I do. Using our duct tape to the top of the CD, it'll actually peel the inside reflective surface. Now, this is actually what all the data gets stored on. And if you have some left over, you can tear it off again. Now I have a complete clean piece of CD for this project. Fun side project. This is a great reflective surface for some decorations. Once we have all of these pieces prepped, we can start working on our project. First thing we need to do is, just like this, it has a small little slit for just a little bit of light to come through. We're going to make a small little slit through this big open hole using business cards are fine. This is just some old flyers. Anything that has a nice thick hard edge, and I use the flat ends. We're going to want to place this on the ground so there's just a small slit, maybe the width of a penny or a nickel. Once you have this, you're going to place it right over top and just fold the edges down. Now, we can trim it, we can fold it, we can do whatever we want. For this project, I'm going to trim it a little bit. The rest of this, we're going to duct tape squarely and securely to the surface. Make sure as you're taping this, you still see the small slit. To make this spectroscope work the best possible way, you want to make sure that the slit is really, really small. So we're going to start covering this in duct tape, not only making a much smaller entry point for the light, but also preventing any other light from getting in. Don't be shy, this project might use a lot of duct tape. Now, it's best to fully tape all of these down, but for this project, we're going to make it go a little bit faster. As you can see, there's a very small slit for this light to enter through. CDs, this type of plastic, kind of looks reflective, a bit rainbow, just from me moving it back and forth. This is called a diffraction prism or a diffraction gradient. There's a specific polarization of lines here in plastic that you can't see or feel, but trust me, it's there, you can see it. Now, we need to make sure that it lines up properly with this orientation of the light slit. So before you tape it on, you're going to want to look it up at a light and rotate it until you see a big square rainbow. That's how you know it's in the perfect orientation. Right here, we'll tape it in position. Once you have found the perfect orientation, we're just going to take our duct tape and cover it to where there's just a small little window for your eye to see through. Remember, the least amount of light coming in you can see the components of that light source a lot clearer. In science, we call that excess light noise. Parents, if you're afraid of any pokey section, you can always cut them off with your scissors. Usually covering them with enough duct tape or thicker duct tape, you won't have a problem. Now, if you don't like the beautiful look of gray duct tape, you can always take a nice piece of construction paper, wrap it around, and that'll even prevent the excess light from getting through the walls of our spectroscope. And just like that, once you've prevented all the other lights from getting in, you have a beautiful spectroscope that you can now separate out the individual wavelengths of light to see, does it have 3 bands, 7 bands? Is it almost a complete rainbow? Notice some of them might be just missing a little bit of blue or green. We have many different kinds of light, and once you learn a little bit about chemistry, you'll notice that that's actually the fingerprint of the atoms that are inside the light bulb. So we can tell what is even creating the light just from those wavelengths. Science is a process to discover everything we want to know about the world around us. We use this process of science to test out and study the light, not only coming off our sun, but coming off of all the light bulbs around us, using these simple ideas of filters, cups of water, and building your own spectroscope. There's even a lot of light that we can't see in the complete electromagnetic spectrum, from the radio waves that give us our internet, to microwaves that heat up our food, to UV rays that give us sunburns. There's lots of more labs that you can use to study the world around us, even the stuff that you can't see. Happy sciencing!